That is the icon.
Oh, yes, correct. Thank you very much. Okay, and can you see my screen now?
Yeah, it's visible. Okay.
Perfect. So thank you very much for inviting me to this symposium. I'm glad to be back in Singapore virtually, unfortunately, but I'm really happy to talk to you about some results, research results I've been conducting in my current position as a regulatory affairs manager for the EMEA region at Stepan Company. So can microplastics biodegrade in the marine environment? And I've used that background picture being provocative because we're not seeing, of course, microplastics here. You're seeing macroplastics. And I will talk to you also about polymers in the marine environment. Just one slide for about Stepan. Stepan Company is a global company with some factories in Singapore and the Philippines and in Europe and in America, which manufactures chemicals that will go into other chemicals. So it's a specialty chemical company, and there's a number of applications that Stepan is serving. You can see some of the pictures here, serving the personal care industry, the food nutrition, agricultural solutions, and the panels of the construction industry. So we want to provide innovative chemical solutions for a cleaner, healthier, and more energy efficient world. And that's the only corporate slide I'm going to show you. The second one is something that is very much part of my motivation of talking to you today, and what makes me wake up in the morning with a smile on my face is that I really think that regulatory affairs are contributing to several sustainable development goals of UN. When we talk about water sanitation, food hunger, food security, biodiversity, climate change, the more information industries can bring up about their products, about how their products behave in the environment, or what kind of they draw, and the more we are contributing to those goals. So the microplastics is a worldwide topic, of course. In Europe, in the EU 27, they've been working on microplastic restrictions, try to restrict the putting on the market microplastics, and they have developed a definition which is still under draft. Should be out sometime in 2022. But the microplastics are considered a solid particle containing minimum 1% weight of persistent synthetic polymer with a size range between 100 nanometers and 1 millimeters. So just to go back on the previous questions, whether it was synthetic polymers or natural polymers, here the restriction focuses only on synthetic polymers. Well, we all know that some polymers in nature can be also very persistent, and we can have a discussion on that in the panel afterwards. So that is important, and there are some criteria in the regulation, in the draft regulation, to derogate to the restriction, and some criteria are linked to the solubility of the polymer to become a microplastics, and also some biodegradability criteria. And this is on the latter I will focus today. the discussion. They're starting with a screening test, and I will talk about the OECD 301 guidelines, and I'm just putting just to put in mind the idea of the order of magnitude of the test. It's around $10,000 a test, and the restriction promote also that in case the screening tests are not positive, we can go into higher tests to simulate the fate of the polymers in the environment using ISO methods or simulation tests. And each test is more around 100K US dollars. So of course, everybody will clearly understand that there's a focus on making sure that screening tests are used as much as possible and give as much reliable result as possible. Again, another regulatory affairs slide. It relates here to the countries around the world who are regulating polymers. You have got 2 blocks or 3 blocks. The gray ones where there's no regulation about polymers here. The green ones which got a registration schemes for the polymers, and that would be USA, Canada, Japan, for instance, Korea as well, Philippines, and the orange one where there's no regulation about the polymer yet, but there's a regulation about the monomers that are part of the polymers. And in Europe, so far, the REACH regulation is focusing on the monomers of the polymers. And this is the polymer definition according to REACH and to the European Chemical Agency, ECHA. It considers, by right, I think, that a polymer is not just a single molecule and long. It's with repeated units. It's a distribution of size and weight of polymers. So it's a kind of mixture of the same molecule of chemical nature, but with different size and weight, but also consists of the intentionally added substances like additives, but also the non-intentionally added substances, the NIAS, which can be the monomer residues, for instance. So this is very important for a regulatory person with an ecotox background, is to understand that definition and that the polymeric substance is that kind of all the chemicals that can go under that definition. And when we talk about a degradation of polymers, of course, we think about abiotic factors and biotic factors. Biotic factors can be mechanical, and you stretch, you squeeze, you tore the polymers because of the application itself or because the environmental conditions. Can be photodegradation, can be thermal, can be chemical. And all the above factors can act in synergy, but will have an effect, will likely facilitate the microbial action, which may follow that degradation. And when we talk about biodegradation of polymers, we're talking about the biotic degradation, but it consists also of 3 different processes, which are first the biodeterioration of the polymer surface by microorganisms because of mechanical actions of the microorganisms, but also some chemical actions, then the biofragmentation due to enzymes secreted by bacteria, and finally the mineralization, meaning that all the polymer will be assimilated by the bacteria or the microorganisms and then transformed into CO2 and water. And this is on the right side. This is a diagram, a flow diagram that my students working on the polymers have been able to draw after a literature review. And I keep it because it's very symptomatic of scientific questions that is beneath all that topic. So it is in French, but I'm sure you all understand that. It's assumed that the polymer will degrade back into monomers, and then the monomers will be digested by microorganisms, and that will be mineralized into CO2 and water. So assuming that the biodegradation potential of a polymer depends on the biodegradation potential of monomers. And this is the big question. Are the polymers degrade back into monomers? So on the upper right of the slide, monomers can be seen as blocks, yellow, of different nature, yellow, green, red, blue, and will be assembled, polymerized, and provide a huge variety of molecules for a huge diversity of application. And then the question is, can it go back? If you take a pencil made of plastics, can it go back to the initial monomers? And having listened to some of the presentation before and what we can find in the literature, there are some data showing that there are some monomers leaching from the polymers, but there's no real trend, to my extent, showing that that the polymers are going back to the monomers. And remember, under the definition of Oecd and REACH regulation, a polymer contains already some residues of monomers, so it's part of the polymeric substance. Now, looking at how the industry react to the regulation and launch some regulatory tests to understand the biodegradation of a substance. I'm not talking here, this slide is not focusing specifically on microplastics and polymers, but on any kind of substance. Is the first test is the readily biodegradation test, the OECD 301, which is very popular. It's a screening test, and basically we're trying to understand. I hope you can see my mouse here. We're trying to understand what will be the fate of the chemical in the environment, and understand how it will be degraded by water treatment plants. And of course, we're doing that in the lab, not in a water treatment plant. So this is a picture of how looks a biodegradation test in real life in the lab. And there is a number of different protocols applicable because of different nature of substances. There are all 301 OECD test guidelines, but they are called A, B, C, D, E, F. And they're all the endpoints considered can be the CO2 evolution or the oxygen consumption, dissolved oxygen, etc. And it's important to look to really understand that biodegradation test. It's standardized. There are very stringent guidelines, which is full of sense. So you want to make sure that the only organic matter that the microorganisms will have to digest are coming from your substance. You make sure that the microorganisms are naive, have never digested that substance before, and you need to pay a lot of attention to the biodegradation curve, and usually the test lasts 28 days, and it needs to pass a level of 60% or 70%, depending on the endpoint, to be concluded as really biodegradable. I forgot something very important. You need also to pass the 10-day window when you're not a surfactant. And that 10-day window starts when you have 10% biodegradation and ends 10 days after. And within 10 days after the first 10% biodegradation, you need to reach that pass level of 60% or 70%. So it seems to be quite easy in screening, but actually, when you look at the details, it's a very interesting test to run, and there's a lot of information you can take out of it. And this is basically what we have done so far. We've tested with the polymers that Stepan is manufacturing. We've tested them according to these OECD 301 test. But instead of ending it at 28 days, we've extended it to 60 days or to 90 days, depending on what curves we were expecting. And we used the 301F, meaning that we used the O2 consumption. We were monitoring with probe O2 consumption in closed bottles, and used a inoculum, so a microorganisms community coming from a domestic water treatment plant. So this is how we can ensure that they are naive. They never digested them before. And we follow the O2 consumption day after day. And this is, I'm going to show you a series of slides here, a series of results. I will not talk about the chemical structure, but it will show that by extending the test by 60 days and doing a little bit of other adjustments, we can have very interesting conclusions on the degradation of the polymers or the microplastics in the environment. I need to add that those tests are in microorganisms and fresh water. I will not show you, but I will because I don't have enough data. But there are some protocols that we've been using also for biodegradation, for studying the biodegradation in seawater, and we've got also some very interesting results that will come into publication in the coming year. So, for instance, we have here a polymer, which I'll show you. They're all the same. So you have the blue curve, which is a reference control. Sorry, that blue curve here. Where's that blue curve here? And this is done in duplicate. So we've got the blue curve here and the brick red curve here is the reference control. It's a chemical that we know degrades pretty well, and it's used to ensure that our test system works. And you can see that it really got a steep curve here, starting a curve, and ending up above 100%, but ending up is above 60 or 70% the pass level, so it's a reference control. Why it's above 100% of biodegradation? These are artifacts of the calculation and the analytical methods, but for those who are more comfortable with chemical analysis, this is very similar to when you try to understand the recovery of your method. You can have values above 100%. So it's not a problem to have over 100% biodegradation here. What is important is what happens before. And then if I look back at the test substance, the test item, that has been done in duplicate, and there you see there is no biodegradation at all. That means the bacteria community find the way to degrade that polymer. When you look at those results, you have to think. You need to think like a scientist. It's not just a result you take for granted. What can happen here, of course, is that the polymer is toxic to the bacteria. So the bacteria are not active because they're all dead. And this is why you have a toxicity control here as well. And that curve shows that there's no toxic effect of the polymer to the bacteria community. So all those tests have been done under a good laboratory practices according to the OECD principles. And so they are considered as reliable, repeatable, auditable, and used for regulatory purpose. So in this case, that polymer found not to be biodegradable at all. And the next one, we got it's a different polymer, and you got a very different curve. The reference is still showing that that the test system is working. The toxicity control is still showing that there's no toxic effects of the bacteria. And you see the test item groups, yellow and gray, and you see a curve which goes quite quickly over 70% at 28 days. It's 71.8%. And when you extended it at 60 days, it goes even up to 80.3%, but you can see already a plateau happening here. And in that, with those results, we can conclude that that polymer is readily biodegradable after 28 days, according to OECD 301. So that's two extremes. With the new protocols developed, you can already figure out the ones which are not biodegradable and the ones which are readily biodegradable. You can also see on one polymer, we've seen that after 28 days, we didn't reach the 60% pass level here. It was 53.8%. So if we had only done a normal OECD 301 test, for example, terminating the test at 28 days, the conclusion would have been that polymer is not biodegradable, readily biodegradable. And this is an important scientific insight here. Until now, there's no real intermediary conclusions between readily biodegradable and persistent. There are some tests available on the market to do those, to investigate further, but they are very expensive and using radioactive elements. Here, just by extending it up 60 days, you can see that we've reached the 84.4% of biodegradation. And that enabled us, according to the different guidance documents, to conclude that this polymer is biodegradable, is reach a value of above 60% after 60 days, according to an Oecd 301. It's not really readily biodegradable, but it's biodegradable, meaning it's not a persistent synthetic polymer falling under the microplastic definition. And finally, you have this this result, another one, which is interesting because we've extended that to 90 days. The reason for that is that we saw a very good start of the biodegradation. At 28 days, it was already 39.4%. So remember, keep in mind that we need to reach the 60%. So we extended it, pursued the measurements, but at 60 days, biodegradation was 42.5%. So there was a plateau reached already, and at 90 days, 45.8%. So the conclusion was that it was not biodegradable, but also what is interesting to see here is that very likely the biodegradation we observed here, because we observed some real biodegradation, but up to 45.8%. What we've observed here was the degradation either of the residues of monomers in the polymeric substance or the function reactive groups of the polymer, which are like a comb. If the polymer is like a comb, for instance, or the branches of the polymer that are listed here, but the skeleton has not been digested. So that means that protocol is very insightful. It gives a lot of very good information, and that will be the last slide of my talk. Is scientifically based extended standard guidelines, the one we've used here, according to the guidance document available, are relevant to understand the fate of the microplastics or the polymers in the environment and in fresh water, or as I've mentioned before, for some of them we did that in marine water as well, and it works. When I say it works, I mean it enables us to define which polymers are persistent or non-biodegradable from those who are biodegradable. But we are only looking here at only one of the biodeterioration is the mineralization in the assimilation. If you remember that slide where I talked also about the biofragmentation and the biodeterioration, these are steps also attributed to the bacteria, but for which there's no standardization yet, and I don't think there is even some methods available. So maybe this is an area of interest for the academics and the policymakers. Is do we need to have some standardized method to understand better the biofragmentation and the biodeterioration of the polymers? Then when we are looking at at that kind of test. I haven't shown you anything about the chemical structure behind, but of course at Stepan we are working closely with the chemist, and we know the chemical structures, we know the monomers, we know the polymerization reaction, the catalysts, the additives, etc. And that allow us to better understand how all those factors behave or drive the biodegradation, and to finally help us to design biodegradable polymers. And what happened here? What was very obvious is that in all the polymers we have tested, some of the monomers were biodegradable, some were not, and it was obvious that the monomers are not driving the polymer fate. It's more about the above factors I'm mentioning, and also the assemblage. In one of the polymer we tested got the same monomers but different sequence of polymerization, and they had very different biodegradable biodegradability behavior. Sorry. And that's extremely important to understand in the view of the microplastic restrictions, but also in the view of the coming regulation, which is around the corner in Europe, which is a regulation about the restoration of the polymers themselves. So we need, with those results on those polymers in those conditions, it is obvious that the polymer's fate is not driven by the fate of the monomers, the nature of the monomers. And of course, the subsequent question is it the same conclusions for when we talked about the effects, the toxic effects, ecotoxicological effects or toxicological effects? And having said that, I thank you very much again for your attention, and very pleased to answer some of the questions.
Okay. Thank you, Dr. Matthieu. Very nice presentations, and very insight into that one, biodegradation of these polymers, and also you talk about the different polymers, some of them biodegradable, some of them. So these are all commercial polymers you tested, or it is randomly picked up, branded or something like that?
No, they're all commercial polymers.
Okay.
In that first phase of the program, but in subsequent phases, we will now the regulatory affair people will now help the R&D people to design biodegradable polymers. So working on polymers under development.
And your topic is marine. I thought, is there any control of salinity or oxidation? Because marine environment is very complex. I thought that may be help to degrade more polymers, or I don't know, because it is having a different ORP, dissolved oxygen, temperatures.
Yeah, that's a very nice question, and actually this is what I like about regulatory affairs, being at the frontier between regulation and science. Of course, the science has helped the policymakers to build some regulation, but once the regulation is here, then there are some other questions that arouse, and these are gaps for research to investigate in. And I've got the exact same question. I haven't read again in the context of responding to the regulation how those factors are taken into account. However, when we run a biodegradation test in marine water, we're not using any inoculum. We're not sampling inoculum from a water treatment plant. We are using the bacteria, the natural bacteria community of the water column.
Okay.
And and we are also aging that marine water to make sure that the only organic matter that will be digested by the bacteria potentially in the test will be the organic matter coming from the polymer. You can extend it to 60 days. This is a protocol which is still under discussion with the countries, the stakeholders of the OSPAR Convention of the Northeast Atlantic. But it shows that under constant conditions of temperature, oxygen, salinity,
Okay.
That protocol can work.
Okay, thank you. That's the one question for you. I would like to know your point of view whether the manufacturer should label the percentage biodegradation on the plastic under different environmental conditions.
When companies like Stepan put on the market a chemical, it comes with a safety data sheet. This safety data sheet is almost a legal it's a legal obligation, and it's a legal document where it states all the product safety information, including the information related to the environment, and that you will find in section 12 of all safety data sheet of all chemical companies. It is the information you can find. It is required to provide information, but it is not mandatory everywhere to do some tests to provide that information. However, in regulated regions like in Europe, for instance, you have to run some biodegradation tests on the chemicals you're putting on the market. So you will find those results in section 12 of the SDSs. However, when it comes to polymers, because they are exempted from the registration in Europe, usually, very, very, very often, you will not find that information because it doesn't exist. This is why the European Union has launched that polymer requesting registration regulation that will come in 2024 around that date, to make sure that data and reliable data of safety data are generated for the polymers that are put on the market.
So our last question, are the industries are trying to move towards biodegradable polymers?
Sorry, say again?
Are the industries trying to move towards biodegradable polymers?
So the short question is yes, but the underlying question here is, do we want to live in a world where polymers are all biodegradable? I'm saying that because there's a notion behind biodegradable, like it's not sustainable. It will deteriorate in time. And when you want to build a building, you don't want that building to degrade with time. You want it to be sustainable, for instance. I'm taking a building because it's a very iconic for my purpose here. But there's other applications where you don't want a polymer to be degradable easily. So there's a balance to find here. But when what is important is when your polymer will end up in the environment, because it helps agricultural solutions, it helps oil and field exploitation, for instance. Then there are more and more incentive to develop biodegradable polymers.
Okay. Thank you, Dr. Matthieu. Thank you for a nice presentation and detail. And we'll move on to maybe the last one. Is there any presentation next? So, Ms. Ramdeer
Yeah, I think he is not there. So I think we are ending the session with this.
Okay.
I think Mr. Param will do the vote of thanks. Then we will move on to the panel. Yeah, Mr. Param.
Okay, thank you very much, all the speakers and from the chair of the session for excellent presentation. Thank you all. It's a really good discussion on this subject and the toxicologies and also the various biodegradable issues. Thank you very much all. And now we end the session and we will move to the final session that is on the panel discussion. I will move all of you to the panel discussion. Thank you all again.
Thank you.